Spectroscopy is the scientific study of the interaction between matter and electromagnetic radiation. It involves the analysis of how matter absorbs, emits, or scatters electromagnetic radiation to gain insights into its composition, structure, and properties. This branch of science bridges physics and chemistry, offering profound implications in fields such as astronomy, biology, environmental science, and materials research. The term spectroscopy originates from the Latin word spectrum, meaning appearance or image, and the Greek word skopēin, meaning to observe. Early studies of light spectra by pioneers like Isaac Newton and Joseph von Fraunhofer laid the groundwork for modern spectroscopy. Over time, advancements in technology have expanded the scope of spectroscopy to include a broad spectrum of electromagnetic waves, from gamma rays to radio waves. Electromagnetic radiation spans a wide range of wavelengths and frequencies, collectively referred to as the electromagnetic spectrum. Each region of the spectrum interacts with matter in distinct ways, giving rise to different spectroscopic techniques. The electromagnetic spectrum is divided into several regions. Gamma rays are extremely high-energy radiation, with wavelengths less than 0.01 nanometers, used in nuclear spectroscopy to study atomic nuclei. X-rays are high-energy radiation with wavelengths ranging from 0.01 to 10 nanometers, utilized for material analysis and medical imaging. Ultraviolet radiation has wavelengths ranging from 10 to 400 nanometers, and UV spectroscopy is widely used to study electronic transitions in molecules. Visible light has wavelengths ranging from 400 to 700 nanometers, and visible spectroscopy explores the absorption and emission of light in this range. Infrared radiation spans wavelengths from 700 nanometers to 1 millimeter, with infrared spectroscopy investigating vibrational and rotational transitions in molecules. Microwaves have wavelengths from 1 millimeter to 1 meter, and microwave spectroscopy is used to study rotational transitions and molecular structures. Finally, radio waves have long wavelengths exceeding 1 meter, with nuclear magnetic resonance and electron spin resonance spectroscopy falling under this category. At its core, spectroscopy relies on the interaction between matter and electromagnetic radiation. These interactions depend on the energy levels of the particles in matter, such as electrons, ions, or molecules. The fundamental principles of spectroscopy include energy quantization, where matter exists in discrete energy states. When electromagnetic radiation interacts with matter, energy is absorbed or emitted as particles transition between these states. Absorption occurs when matter absorbs radiation, transitioning from a lower energy state to a higher energy state, with the absorbed wavelength corresponding to the energy difference between the states. Emission happens when matter transitions from a higher energy state to a lower energy state, releasing energy in the form of electromagnetic radiation. Scattering refers to radiation being scattered by matter without significant energy transfer, as seen in Rayleigh and Raman scattering. Lastly, selection rules dictate that not all transitions are allowed, based on quantum mechanical principles that determine the transitions that can occur. Different spectroscopic techniques are based on the specific interactions between matter and electromagnetic radiation. These techniques include atomic spectroscopy, which focuses on the analysis of elemental composition through electronic transitions in atoms. Subtypes include atomic absorption spectroscopy, atomic emission spectroscopy, and atomic fluorescence spectroscopy. Molecular spectroscopy studies molecular interactions with radiation, focusing on vibrational, rotational, and electronic transitions. Examples include infrared, Raman, and UV-vis spectroscopy. Mass spectroscopy, though not based on electromagnetic radiation, analyzes charged particles based on their mass-to-charge ratio, providing structural and compositional information. X-ray spectroscopy investigates inner shell electronic transitions to study elemental composition and chemical states. Nuclear magnetic resonance explores the interaction of atomic nuclei with radiofrequency radiation in the presence of a magnetic field, revealing structural and dynamic information about molecules. Raman spectroscopy measures inelastic scattering of light to study molecular vibrations and chemical composition. Fourier transform infrared spectroscopy uses infrared radiation to analyze molecular vibrations, providing insights into functional groups and bonding. Spectroscopy plays a pivotal role in numerous scientific and industrial applications. Some of its key applications include astronomy, where it is fundamental in determining the composition, temperature, and motion of celestial objects. Techniques like Doppler spectroscopy have been instrumental in discovering exoplanets. In chemistry, it is used to identify chemical compounds, study reaction mechanisms, and determine molecular structures. In biology, it helps in understanding biomolecular structures, enzyme activities, and cellular processes. In environmental science, it analyzes pollutants and monitors air, water, and soil quality. In medicine, it is applied in diagnostic imaging, such as MRI and CT scans, and in drug discovery. In materials science, it investigates the properties and structures of materials, aiding in the development of new technologies. Recent technological advancements have revolutionized spectroscopy, enhancing its sensitivity, resolution, and applicability. Innovations include laser spectroscopy, which provides precise and high-resolution measurements using coherent light sources. Time-resolved spectroscopy studies dynamic processes by analyzing changes over time. Portable spectrometers enable on-site analysis in fields like environmental monitoring and food safety. Machine learning integration enhances data analysis, enabling the extraction of complex patterns and predictions. Spectroscopy is a cornerstone of modern science, offering unparalleled insights into the fundamental properties of matter. Its diverse techniques and applications continue to expand, driving discoveries in physics, chemistry, biology, and beyond. By leveraging the interaction between matter and electromagnetic radiation, spectroscopy remains an indispensable tool in unraveling the mysteries of the universe.